In the previous part, we had looked at the attach procedure from a point of view of identities which are created or the connections that are created. And that's important because a mobile is going to be connected to a network for a long period of time. And so these connections that are created enable the nodes to send messages to each other regarding this UE in a much simpler way. Now we look at the same attach procedure from another angle, and that's the call flows, and that's how messages are sent between nodes and what those messages contain a little bit and what the main functionality is. These call flows are the main way in which the system has been specified in the LTE specifications. So it's good for you to get an idea about what these call flows are and what they mean. Of course, these standard specifications doesn't have as much color and as much animation that these slides here are for. Well, that's why you're probably listening to this. Well, the first thing that the mobile does, it comes into the network and it starts listening to seeing which is the closest or the best base station that the mobile can communicate with. And based on the signal that it measures, it picks up a particular base station, and that's the base station that we are showing over here, the E node B. And the first thing that it does is it sends a random access preamble. It sends a really short message and says, hey, I'm here. I want to speak. Hey, hey. So what the thing is, this random access preamble actually consists of two parts. One is the preamble identity, and which is called the RAPID, RAPID, random access preamble identity. Okay, preamble identity. This is one of 64 values that the mobile can choose. So it picks up one of these 64 values and says, psst, psst. Now, the other part of this information, which is very important, is the time and frequency in which it is sending this message. So if this is time and this is frequency in the uplink direction, this mobile will pick up one of these 64 values. Let's see, it picks up value 22, and he's going to send out this value 22 in this time frequency slot. So this is 22 in here. And he picked up this time frequency slot. Let's take another mobile, which is also in the same network and wanting to communicate, also set up a connection. He picks up another value, and for this case, let's assume that he picks up the same value, 22. So he sends a value 22, but he picked up, luckily and by chance, he picked up another time frequency slot, which is not overlapping with the time frequency slot of that our mobile used. So the time frequency slot, the identity of the time frequency slot, has been given another name, which is called the RARNTI, which is the random access radio network temporary identity. So the time frequency slot in which the mobile sends its communication also has a meaning and has a value that gets used in the random access procedure. So this message comes to the base station. The base station listens to it and then sends back a random access response. And the random access response contains a temporary identity that is providing. It also contains, obviously, the rapid value which it had received and the RARNTI value. So the base station kind of sends back a random access response saying, hey, hey, you who transmitted number 22 and who transmitted in this time frequency slot number, whatever number it comes out to, 6,000. I'm giving you this temporary identity, and let's call this temporary identity, as we had kind of in the previous one, I'm giving you a temporary identity, Ashok. So you are Ashok. Now, what happens is if there are two people, if both Ashok, if there were two UEs that transmitted at the same time, they would both think that, hey, they're Ashok. So now there are two Ashoks over here. So these both Ashoks will go ahead and then send a third message, which is this radio resource control connection request, and says, hey, I want to connect to you and you sent me this particular CRNTI. So there are two Ashoks, as we said. There is Ashok 1 and Ashok 2, who unfortunately in this case had transmitted with the same rapid and within the same time frequency slot, and so they collided. Now this message which is coming from these two Ashoks out there will collide at the E node B. They have slightly different information in there, and the probability of both of these messages succeeding at the E node B is very low. And if such a collision occurs, there will be no response coming back from the E node B, because it would never be able to decode this message correctly, and hence both the Ashoks will time out and they'll go back up and go back into the random access procedure. But instead, if either the rapid or the RA-RNTI were different, so either the preamble chosen or the time frequency slot in which they had transmitted this preamble were different, then one of them would be successful, and if they are successful, they will get back a response saying, yes, this is a connection setup. I had given you this temporary identity called Ashok. So now this temporary identity is essentially your CRNTI, your cell radio network temporary identity. So at the end of this random access procedure, there has been now a connection that has been set up between the mobile and the base station, and an identity, the CRNTI, has been established for this mobile. Once it gets this RRC connection set up, the mobile goes ahead and responds with a connection complete message. And this connection complete message is the fifth message that is being sent. And a lot of these radio geeks, when you talk to them, they'll go and say, oh, something comes in message 5 or something comes in message 3. So message 3 is this message which was the connection request message, and message 5 is the message that is after the random access is successful and the radio resource control channel has been essentially set up. This message, because of the way it's transmitted on the air, has to be very small. I mean, there are some size limitations, and you really cannot have much information in here because of the way that the channel is set up for sending these messages. Obviously, random access messages are also tiny. So you have tiny message, you have small message, and message 5 can be a big message. I mean, there is no problem here. Obviously, there are some signaling channel limitations, but you can here send in your NAS message, which is this attach request message, and PDN connection setup message, and these are two different messages. And a little bit later in the slide, we'll look at why these are two separate messages. One is saying, okay, I want to attach. The other one is saying, give me an IP connection, and you would be saying, why not just send one message? So we will cover that. We'll provide you the secret to that in a few minutes. All right, and this procedure by which the radio resource control signaling has been set up is called the RRC setup procedure. And as you can see, it is the random access procedure actually goes to 4 messages, and then the radio resource control setup procedure is everything that starts from connection request and that ends with a connection complete. And so we've completed this, and now we are now on to the next step, and this message has come to the E node B, and we have seen those two attach requests and PDN connection requests. And this base station goes ahead and says, he picks up an MME, says, I need to send these NAS messages to the MME. It'll go ahead and send what's called an initial UE message, and it puts both the NAS message, the attach request message, and the PDN connection, and sends it to this MME. And then in the previous slides, we had covered how it's setting up these identities of S1 AP identity, and then we will. So it's basically telling the MME that if you really want to send a message to me, send it to this E node B UE S1 AP identity, and this we had covered in the previous part of the slides, and we won't kind of go into that part over here. For keeping up with that, you can go back to that previous part and take a look at it. So he goes ahead and sends this initial UE message, and which includes these two NAS messages, and the eNodeB doesn't look into a NAS message. Now, technically, you could say over here that these two NAS messages are actually not encrypted or integrity protected. So the base station could look into these messages and see what these bits are, but the protocol separation says that eNodeB does not look at this, and it just forwards this NAS message to the MME. So when this NAS message comes in, the MME says, "Hey, I haven't authenticated this base station, so I've got this message, what should I do?" It starts the authentication procedure. So it sends an authentication request to the HSS saying, "Hey, this is the IMSI, I want, please authenticate it." And the HSS, the subscription data, kind of looks at the IMSI, says, "Aha, okay, this IMSI is really paying it's really my mobile. I have his subscription data with me, but I need to make sure that this is actually Mehmet who says who's Mehmet." So the IMSI is saying this is Mehmet, but anybody could go ahead and says, "Attach, I'm Mehmet," and there you go. And if the system just accepts you, then essentially poor Mehmet will be paying the bills, and you will be doing all the browsing to the internet, and we don't want to have that to happen, right? I mean, especially the operator doesn't want it, and Mehmet doesn't want it, because Mehmet will refuse to pay his bills. So the HSS goes back and basically provides some keys and provides some authentication parameters. It provides a random value and also tells the MME that you should expect this response. So send this out to the mobile, and if you get this response, it's authenticated. That's at the highest level. We will look at security in a little bit later slides. So once this message comes back, the MME goes ahead and sends this authentication request message and sends what's an authentication token that had come in from the HSS, and also this random value which we said. The eNodeB goes ahead, processes this information, sends back an authentication response, and that includes a value res in there. And as we said, this xres is not passed to the UE, and if this res is equal to xres, hey, the authentication is successful. So that is at the very highest level how authentication is being done of the mobile. Some key is being provided, a random value and an expected response is provided, and if the UE responds with that same number, this is the UE, because nobody other than this mobile could have created this response from this random value. Obviously, if you're not Mehmet and you got this random value, you could try your luck in sending in a res, but your res would not, with a very high probability, not match the xres, and the system will say, "Sorry, you're not allowed to browse the web." But let's assume that this is now successful over here. So we have essentially authenticated the user that this is really Mehmet, who he says it is. But one thing is, we still haven't figured out what the encryption or integrity protection protocols are going to be. This is just saying, yes, this res is equal to xres, and yes, you are Mehmet. But in the next part of the communication, what's happening is a security mode command, and that is where the algorithms for the algos for encryption and integrity protection. So encryption is when you hide the message. You basically take a message and turn it around into something that's garbled, nobody else other than the mobile can understand. And then you also do integrity protection, which is essentially saying that if somebody else modifies this message, I will know that it's being modified. So if some bad guy over here tries to modify the message, I'll know that it's being modified. So both algos for both of these, encryption and integrity protection, are negotiated between the MME and the mobile. And the security mode command that comes back is over here. We are showing it kind of in a hashed manner, which means it's encrypted. That means you really can't see what's in here. And the signature means that if you modify anything, I'll know. So this is integrity protection. That's the way I'm kind of showing it, and you'll see this in some of the later slides also. So this is encrypted, this is integrity protected. So we have NAS security, which is set up, which is both set up the encryption and integrity protection. And in the security, you'll see there are two separate keys for it. That's why we are showing two keys. One is for an encryption, the other is for doing integrity protection. And we essentially have the so-called non-access stratum security, which is set up. And just bear with me for a little bit for about what the heck is non-access stratum, but it is just a hint. It's a communication between the UE and the MME, or the mobile and the MME. All right, so we have authenticated the UE. We haven't yet authorized the UE, and that part of the authorization, which says what kind of services is this mobile allowed to receive. And for that, there is something called a location update request message that goes to the HSS saying, please give me the subscription data of this mobile. And there are two purposes of this location update request. One is to request the subscription data to say what kind of services, and obviously you're thinking, what do you mean by services? And this is a data connection, I need data. Yes, so data connectivity is one request, is one service. Also, for example, whether the UE is allowed to receive SMS or not. I mean, in all networks today, SMS comes as a given, but also in the subscription data, you could have what other services are there, and it'll basically provide some information also as to what is the overall gigabit that the mobile can have, has in its subscription. So if I've paid 15 Turkish liras to my operator, I'm probably getting something like 1 gigabit in a month. And if you're paying 550 Turkish liras to your operator, you're probably getting 10 gigabits in a month. So that kind of information comes down in the subscription data. And also the other part of this location update request is to tell this HSS, this subscription subsystem, that this is the MME which is serving this mobile, and this information is actually used a little bit later. The HSS stores which MME is serving the mobile, because if some SMS needs to be sent, the query gets sent to the HSS to say, okay, where do I send the SMS to? And it needs to come to the MME. For IP packet data, you don't really need to know which MME is serving the mobile. So anyway, so we've gone ahead and we have authorized the UE also. So we've gotten subscription data, and then we figure out, yes, he has paid his bills, he's allowed to get data access. Or it may have come back and said, oh, he hasn't really paid his bill. It's okay that he's authorized. This is really Mehmet, but he hasn't paid his 15 Turkish liras a month, so don't give him any data services. So that's the authorization part of it, and that gets done with this location update request response message. And now we come to the next part of the flow, and that's kind of setting up the S5 and the GTPC tunnels that need to be set up. So the MME goes ahead and is setting up the GTPC tunnels, which are going to be one between the MME and the serving gateway, and also the GTPC tunnel gets sets up between the serving gateway and the P gateway. And also you have the user plane tunnel that needs to be set up, and this is the EPS bearer, as we said, and this is the EPS bearer ID 5. Which gets set up, and the tunnel IDs kind of get set up, and that part of tunnel IDs we had talked about in the previous slide, so we won't go into this over here. And so you end up kind of getting back a create service response where these tunnel IDs have been set up and completed. So the S5 bearer is set up both the control plane and the user plane. Once this happens, now that the next part of it is setting up the radio channel and the data radio bearers and the S1U. So we still haven't set up this connection between the serving gateway and the E-Node B, and obviously we haven't set up anything for the data radio bearers. We had the signaling bearers which had been set up, or at least one signaling bearer, and we had the NAS security which has been set up. So with this initial context setup request, this is the information telling the E-Node B, go ahead and really start communicating with this mobile. He has been authorized, he has been authenticated, now give him a data radio bearer. The E-Node B, before it gives it a data radio bearer, goes ahead first, kind of says, I need to set up a security on my own with this mobile. So the way the system works is that there is security which is set up between the E-Node B and the mobile also, and that is called the access stratum security. And essentially the way it gets set up is that we have a security mode command, just like in the previous case, except that this is for at the access bit. This is the radio resource control part of it. This is between the UE and the E-Node B. So at the end of this handshake over here of the security mode command request and complete, you end up having encryption and integrity protection for all signaling messages that will go between the E-Node B and the UE. So any message, we had anyway seen that NAS is secure, is encrypted and integrity protected between the MME and the UE, but this encryption and integrity protection are for messages that may start from the E-Node B and go to the UE. For example, asking the mobile to go ahead and make some measurement reports, or asking for some specific information from the UE. And that, for example, the very next thing that happens after here is that the E-Node B goes ahead and asks for the UE for its capabilities. That says what kind of frequencies it can work in, what kind of modulation rates it can use, blah, 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 a whole bunch of radio capabilities. And in order to keep that secure, we had this access stratum security which had been set up. So now this is secure exchange between the E-Node B and the UE, and we have these messages are encrypted and integrity protected also. After that, we still have to set up the data radio bearers, and that's what happens in the next steps over here. There is a radio resource RRC connection reconfiguration, and this includes these two messages that have come in over here, and this is also asking the mobile to set up a data radio bearer. So that is why this connection reconfiguration is, and it's also kind of piggybacking these two NAS messages to the mobile. And then once the radio channel has been set up, the reconfiguration complete comes back from the mobile. That means the data radio bearer has been set up. These NAS reply still hasn't come back. I mean, so you should keep that in mind. So this says, okay, the radio has been set up. Once the radio is set up, the E-Node B goes ahead and gives the initial context setup complete. He gives a response to this message, and he also provides the S1U TEID that needs to be provided to the serving gateway for creating this S1U bearer. With this RRC reconfiguration complete, now we have the three signaling bearers which had been set up previously, and then we also have this data radio bearer which has been set up between the E-Node B and the UE for carrying the data information that may come from all the way from the internet to the UE. In the meantime, what the mobile goes ahead and says, it processes the attach, accept, and the activate default bearer request. That is the PDN connection request. It says, okay, fine, I've processed these look good to me, and it goes ahead and sends an attach complete and says, yes, the default bearer also, or a bearer for user plane data also has been set up, and it sets a complete message. which comes to the MME. Once these two messages have come in, the MME goes ahead and now completes the setup of the S1U tunnel. And for that, as we had looked at the previous slides, it sends a modified bearer request, and it includes the tunnel ID that the eNode B had provided. So basically all packets coming from the internet to the from the internet to the P gateway will go down this way and then go all the way down to the UE this way. And this is the tunnel ID that will be used from the S gateway to send a packet, to send the IP packet of the user to the eNode B. So we have all of this. Essentially with this, we have the entire tunneling, entire plumbing setup for the mobile, and that is shown in this slide over here. So we've got the main plumbing that is required for the mobile to now do IP connectivity with the network. Now you're saying all of this has happened, but I still don't have an IP address of the mobile. Yes, so that's exactly what happens in the next step. Is once these data radio bearers have been set up, the DHCP client will go ahead and send a DHCP request, which will come all the way to the P gateway. The P gateway can go to a DHCP server and comes back, and this comes back and says, give this mobile an IP address of 10.40.40.4. And that IP address gets provided to the mobile. So now the mobile has an IP address, it can communicate to the world, and now it goes and Mehmet starts doing his browsing of the web or communication with Ayşe, whatever he wanted to do. He has connectivity to the internet from here. Now, one thing to keep in mind is that the IP address, as you've seen, the IP address of the UE is actually not visible anywhere, or is not used in the network anywhere between the MMES gateway and the eNode B. It's only used for it only gets tunneled inside this GTPU tunnel over here and this GTPU tunnel over here, and the radio bearer identities are all 5, as we had kind of seen in the previous message, because the EPS bearer identity starts from 5 and has 8 values and goes up to 12. So anyway, so for this attach purposes, this value is 5.